I am Abdullah Haroon Rasheed, and this is a presentation of our work for learning to measure the static friction coefficient in cloth contact. This work was done at INRIA Grenoble in collaboration with Sorbonne University Paris. The overall cloth dynamics are substantially affected by choice of the friction coefficient. Here we can see that with a lower friction coefficient, on the left the simulated shirt behaves quite differently than the one with a higher friction coefficient on the right, despite keeping other material parameters the same. Measuring friction coefficient of cloth has been a long-standing problem in textile engineering. However, most proposed methods have utilized some invasive technique with a physical apparatus. Our goal in this paper is to measure friction accurately between cloth and a substrate using a non-invasive, video-based technique. For learning friction behavior from video and doing so to a fine level of accuracy, it is not trivial to collect a large amount of real training data that has proper coverage of all possible friction coefficients. Therefore, we would have to rely on simulated data and ensure that training on it generalizes to real test data. In short, in order to train our model, we want to use simulated data that has been generated by a validated physics-based simulator. Thus, we come to the first contribution of our paper, which is physical validation of the Argus simulator. We choose the open source Argus simulator, which is a thin shell simulator from the graphics community that can simulate clothing while simultaneously resolving elastic forces, non-penetration, and Coulomb friction constraints. In order to verify the behavior of the simulator, we recreate an experiment from the physics literature where friction behavior of a thin isotropic elastic strip under negligible effects of gravity has been defined analytically. The black line is the analytically derived slippage threshold by Sano et al. We repeat the same experiment in simulation and calibrate various free parameters of the simulator. We can see here that our validated simulator, which is shown by the purple curve, shows a very good agreement with the analytical black curve. Using our calibrated simulator, we generate our dataset. The dataset comprises of a simple drop and drag motion, which can be easily replicated in a physical setup. We render this motion with 3 viewpoints and 8 random textures on the cloth. We simulate 16 friction coefficients, ranging from 0.0, shown in the top left, to 1.5, shown at the bottom right. In order to test our model, we make an experimental setup to perform a similar drop and drag motion. On the left, we can see the experiment, which shows a clamped piece of cloth on a substrate floor. The cloth can be moved horizontally and vertically using 2 motorized stages. We measure a reference friction value for each cloth substrate pair using the simple inclined plane experiment shown on the right. In our real test dataset, we have 7 substrates and 9 cloth materials. Now we explain our deep learning based model used to predict material and friction parameters. Since our input is in the form of videos, we take inspiration from the model proposed by Donoghue et al. For action classification from video. Our model takes video frames as input. Convolution and pooling layers are used for extracting image features from each frame. Weights are shared between these layers. These image features are then fed to LSTM layers, which extract temporal sequence information. And finally, we have fully connected layers at the end. We train this model separately for predicting either friction or material parameters. One thing we note is that the model performs significantly better on estimating material parameters than on estimating friction coefficient. We use our baseline model to predict material parameters, but to improve friction prediction, we feed these material parameters as an additional input to the model predicting friction to form a conditional friction estimator. This pipeline yields significant improvement in prediction accuracy for friction. And now we take a look at the prediction results of our model. Here we can see various data points from our test dataset with reference and predicted friction values. We measure the error of our prediction from the measurement error range of the reference values. Our model predicts an error of less than 0.1 on 93.6% of our real test data, and an error of less than 0.2 on 100% of our real test data. This work is a first step towards estimation of friction in the wild. Furthermore, in scenarios where capturing significant amounts of real data is prohibitive, we present a protocol to improve simulated data generation by experimental verification. This has interesting applications for other non-invasive measurement problems. Thank you for watching.